All right, so now we're going to identify the symbols and the names of some common elements. I know a lot of people want to know, do I need to memorize the periodic table? I will not ask you questions about memorizing the periodic table. You will have one in front of you most times taking the exam. But what you should know are the symbols. So if C is for carbon, you should know it's carbon. So at least know the first three rows so that you don't have to constantly look back and forth to determine if you have a compound and it's got, you know, some letters in it, you shouldn't have to always look back at your periodic table to see what those are. So we're mainly going to use elements that are I'll say, elements that are in the first three rows of the periodic table. So elements we know are pure substances that cannot be broken down into simpler substances. And they are represented by chemical symbols. And there are two ways, well, there are two different types of elemental symbols. There are one-letter symbols or two-letter symbols. If it's a two-letter symbol, the second letter is always lowercase. And this is important to know because in chemistry, if you write capital C, capital O, you have just written the symbol for carbon monoxide and not cobalt, okay? Know that if there is a two-letter symbol, you have got to make sure that that second letter is a lowercase. Can you guys think of some pure elements that you come across? I mean, there might be some on this slide. What are some of the ones that you know that you encounter in your daily lives? What are some of them? Type them in. Oxygen. Milk is a mixture. Phosphorus. Do we actually come in contact with pure phosphorus? Not generally. Gold, silver. Yeah, if you've got 24 karat gold, you've got a pure substance. Did you guys know that like 14 karat gold is a mixture of gold and silver? So aluminum foil is definitely pure. We don't actually come across calcium in its pure elemental form. Platinum, okay, if you have those platinum rings, maybe, and diamonds, yes. Fluoride, so the ending on fluoride lets us know that that "ide" ending lets us know that that is an ion and not an element. And so some of these things you are talking about are potassium. We don't tend to come across potassium in its elemental form, or fluorine. Those are most likely going to be found in a compound. So most of the things that we come in contact with are going to be found in compounds. Yes, lead, neon, and neon lights. Okay. All right. Good. And what's the gas that goes into those balloons that we buy?
Helium.
Yes,
Helium.
helium. That's pure. All right. So here are some elements that are important for life. Notice that all of these are, the first four are essential. They're found in every living being, and sulfur as well, because sulfur and phosphorus are found in DNA. So every living thing is composed of, we say CHNOPS, CHNOPS, right? Because phosphorus and sulfur are found in all DNA and RNA. So here's a list of some of the important elements and what we need them for. So this says down here, carbon, hydrogen, oxygen, nitrogen are present in most foods. Other elements listed vary in their distribution. The ones that are with an asterisk are called macronutrients, meaning that we need them in our diet of higher than 100 milligrams per day. And there are some that are micronutrients that are needed at lower amounts per day. All right. So here we have our periodic table. Like I said, we generally will use the first 3 rows often. Here we have our 7: nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and hydrogen. They make that 7 on the periodic table, and those are all diatomics. So let me change that. The first 4 rows, we tend to use these atoms often, and you'll see silver and gold in different compounds that we're looking at, but you want to be able to just glance at the periodic table and know what you are looking at. So here are some of the common ones that you might see often. So I wouldn't ask you a question on a test. Ca stands for what? That's not what we're doing here. So I wouldn't ask you to memorize in that way. All right. So table salt is a compound, and sodium and chlorine chemically combine. So here we have sodium metal and chlorine gas. When they come together to make the compound sodium chloride, notice that they have completely different physical and chemical properties. Sodium metal is a shiny, soft, smooth metal where it's a solid, but it's a soft solid. Chlorine is a gas, it's green. But notice that sodium chloride is a white powdery solid, crystalline solid. So they have completely different properties, chemical and physical properties, than the elements that make them up. So let me ask you this. Is sodium chloride the only salt that you encounter in daily life?
No.
No. What do you think are some other salts that you might come in contact with? Sea salt actually is made up of a number of different salts, so it's really a salty people. Funny. So sea salt is made up of a bunch of different compounds, so it's actually a mixture. Epsom salt, yes, I think it's a magnesium salt. Potassium chloride, yes, is actually, some people can't take in regular salt, so they buy potassium chloride. Bath salts have more than one type of salt. So a lot of the things that sodium fluoride, yes, that's a salt. So some of the things that you guys have listed, the Himalayan pink salt is not actually a compound. It's actually
It's a mixture.
It's a mixture of different salts. So Epsom salt is a magnesium, I think it's magnesium sulfate. And a lot of the elements that you guys listed earlier are found in salts, right? So any metal plus a non-metal is going to give us a salt, okay? Sodium is not a powder. So sodium chloride is a white powder. Sodium, if you look on, it's found on the left-hand side of the periodic table, and everything found in those first 2 columns on the left side, those are all metals. So sodium is a metal, all right? So yes, so you can, if you learn the properties of the periodic table, then you will know what is a metal, what is not a metal, and what is a metalloid. So that is what you will learn in Unit 3. Why is salt salty? That's a good question. Not all salts are salty. Yes. Clarify, any metal plus a non-metal equals a salt. Yes, so it depends on what kind of salt it is. There's a lot of salt on the earth, so it's really not that hard to harvest it. So it depends on the chemical properties of the elements. So remember, most of the things in life we don't find in their pure states, right? So it's really hard to find sodium metal and chlorine gas, but it's pretty easy to find sodium chloride, right? So it takes a lot of time, well, not a lot of time. It would take a chemical reaction in order to get these back to their original properties. I wouldn't cook with seawater directly because the salt level is extremely high, and that would not be good for you. And compounds, compounds are made under specific, what's the word I want to say? Conditions. Okay, so that's why it's not necessarily a way, it's not like you could just mix these two together and it automatically happens, right? So sodium is expensive, but salt is found everywhere on Earth. And there are these salt lakes that are used to actually harvest salt, right? So table salt, NaCl, are found all over. So most of these things are made naturally over a long period of time. All right, so what are chemical formulas? Great. So chemical formulas are a way to write, are the way that we can actually, what's the word I want to say? Visualize what a compound is made of. So a formula is a symbol of elements that are combined to form chemical formulas. So H2O represents water, and it shows that we have 2 hydrogen atoms and 1 oxygen atom. Methane is CH4, meaning it has 1 carbon and 4 hydrogen atoms. Here we have, this is sucrose again, where we've got 12 carbon atoms and 22 hydrogen atoms and 11 oxygen atoms, okay? And this would be our chemical formula. Notice that for atoms where we only have 1, we do not write 1 as a subscript. So the subscript tells you how many atoms you have of each element present in the compound. All right.